The universe is a vast and mysterious place, stretching far beyond what our eyes can see and our minds can comprehend. It's filled with countless stars, planets, and galaxies, all moving and interacting in intricate and often beautiful ways. But despite its apparent complexity, the universe seems to follow a certain set of rules, almost like a cosmic dance choreographed by nature itself. One of the most fundamental and elegant of these rules is the principle of least action, a concept that has fascinated scientists and philosophers for centuries. This principle states that the universe, in a sense, takes shortcuts, always seeking the most efficient path. It always chooses the path of least resistance, much like water flowing effortlessly through a landscape. Imagine a river flowing down a mountain. It could take many paths, winding and twisting through the terrain, but it always chooses the one that requires the least amount of energy, the path that allows it to move smoothly and efficiently. This is the essence of the principle of least action, a guiding principle that can be observed in many natural phenomena. It's a powerful idea that has helped us understand everything from the motion of planets in their orbits to the behavior of subatomic particles in a collider. This principle even extends to the bending of light around massive objects and the ripples in space-time known as gravitational waves. By applying the principle of least action, scientists can create models and simulations that predict the behavior of the universe with remarkable accuracy. This principle isn't just limited to the cosmos, it can be seen in everyday life, from the flight patterns of birds to the way plants grow towards sunlight. The principle of least action reveals a profound interconnectedness in nature, showing us that everything is part of a larger, harmonious system. As we continue to explore and understand this principle, we uncover more about the universe's shortcuts, and in turn, more about ourselves and our place in this vast, mysterious cosmos. The principle of least action has a long and storied history. Some of the greatest minds in physics have contributed to its development. It all started with Pierre Maupertuis, a French mathematician and astronomer. In the 18th century, he proposed that nature always acts in a way that minimizes a quantity he called action. Then came Leonhard Euler, a Swiss mathematician and physicist. He further developed the concept of action and applied it to the study of mechanics. But it was the Irish mathematician and physicist William Rowan Hamilton who gave the principle its definitive form in the 19th century. He formulated what we now call Hamilton's principle, a more general and powerful version of the principle of least action. Hamilton's principle goes beyond simply stating that nature minimizes action. It tells us that the path taken by a system is the one for which the action is stationary. This means that the action doesn't necessarily have to be the absolute minimum. It could also be a maximum or a saddle point. The key is that the action remains relatively unchanged for small variations in the path. This might seem like a subtle distinction, but it has profound implications. It allows us to apply the principle of least action to a much wider range of physical phenomena. This includes systems that are not easily described by the concept of minimizing action. Let's consider a simple example to illustrate the principle of least action: tossing a ball. When you throw a ball, it follows a parabolic trajectory. Why does it follow this specific path and not any other? According to the principle of least action, the ball chooses the path that minimizes the action. In this case, the action is a quantity related to the ball's kinetic and potential energy over time. The parabolic path is the one for which the difference between these energies is minimized over the ball's flight. Any other path would require more energy and therefore wouldn't be the path of least action. You might wonder how this relates to Newton's laws of motion, which we learn in school. Newton's second law, which states that force equals mass times acceleration, is a powerful tool for describing motion. But it's a differential equation, meaning it tells us how a system evolves from one moment to the next. Hamilton's principle, on the other hand, is an integral principle. It considers the entire path of a system over time. It turns out that Hamilton's principle is equivalent to Newton's second law. They are simply different ways of looking at the same physical reality. In fact, we can derive Newton's second law from Hamilton's principle. Euler and Lagrange, who preceded Hamilton, made significant contributions to the development of what's known as Lagrangian mechanics. This powerful framework uses the concept of action to describe the motion of systems. It's particularly useful for dealing with complex systems with multiple degrees of freedom. Imagine trying to analyze the motion of a pendulum using Newton's laws. It can be done, but the equations can quickly become cumbersome. Lagrangian mechanics provides a more elegant and efficient approach. By defining the Lagrangian of the system, which is the difference between its kinetic and potential energy, we can derive the equations of motion with relative ease. It's important to clarify that the term least action is a bit of a misnomer. While in many cases the action is indeed minimized, the more general principle is that the action is stationary. This means that the path taken by the system is a point where the action doesn't change much for small deviations in the path. Think of a ball resting at the bottom of a valley. This is a point of minimum potential energy. If you nudge the ball slightly, it will tend to return to its equilibrium position. Similarly, the path of a system described by Hamilton's principle is a point of stability in terms of action. The principle of least action has had a profound impact on physics, extending far beyond classical mechanics. This principle, which states that the path taken by a system between two states is the one for which the action is minimized, has been a cornerstone in the development of physical theories. In the early 20th century, physicists were grappling with the strange and counterintuitive world of quantum mechanics. The classical theories that had worked so well for macroscopic objects were failing to explain phenomena at the atomic and subatomic levels. They needed a new framework to describe the behavior of particles at the atomic and subatomic levels. Traditional concepts of particles following precise trajectories were no longer sufficient. Remarkably, the principle of least action provided a crucial bridge between the classical and quantum worlds. It allowed physicists to extend their understanding from the macroscopic to the microscopic realm, offering a unified approach to both domains. Richard Feynman, a brilliant American physicist, developed a formulation of quantum mechanics known as the path integral formulation. This innovative approach revolutionized the way we understand quantum phenomena. This approach is deeply rooted in the principle of least action. Feynman's path integral formulation suggests that instead of a particle taking a single well-defined path, it actually explores an infinite number of possible paths. It proposes that a quantum particle doesn't follow a single well-defined path. Instead, it takes into account all possible trajectories, each contributing to the particle's overall behavior. Instead, it explores all possible paths, and the probability of observing it at a particular point is determined by the action associated with each path. This probabilistic nature of quantum mechanics, as described by Feynman's formulation, has been instrumental in advancing our understanding of the subatomic world. The principle of least action continues to be a guiding light in modern physics, influencing theories and experiments in fields ranging from particle physics to cosmology. Its elegance and power lie in its ability to connect the seemingly disparate realms of classical and quantum mechanics, providing a deeper insight into the fundamental workings of the universe. The principle of least action is more than just a mathematical curiosity. It is a cornerstone of modern physics, a guiding light that has illuminated the path of scientific discovery for centuries. It's a profound statement about the nature of the universe itself. This principle suggests that the universe operates in a way that minimizes the action or the amount of energy expended to achieve a particular outcome. It suggests that there's an inherent elegance and efficiency in the way things work, from the smooth swing of a pendulum to the effortless flight of birds in formation. Nature seems to follow this principle with remarkable precision. It's a testament to the power of human curiosity and our drive to understand the world around us. Scientists and researchers have long been fascinated by this principle, using it to unlock the secrets of the natural world. As we continue to explore the cosmos and delve deeper into the mysteries of the quantum realm, the principle of least action will undoubtedly continue to guide us. It is a beacon that helps us navigate the vast and often perplexing landscape of scientific inquiry. It's a reminder that the universe is not a random collection of events but rather a symphony of motion governed by elegant and fundamental laws. These laws, rooted in the principle of least action, reveal the underlying order and harmony of the cosmos. Our journey of discovery is far from over. Each new experiment, each new observation, brings us one step closer to a deeper understanding of the universe. There's still so much we don't know about the universe. The more we learn, the more we realize how much remains to be discovered. But by standing on the shoulders of giants like Hamilton, Lagrange, and Euler, we can continue to push the boundaries of knowledge and unlock the secrets of the cosmos. Their pioneering work laid the foundation for modern physics and continues to inspire new generations of scientists. And Euler, we can continue to push the boundaries of knowledge and unlock the secrets of the cosmos. Collaboration and shared knowledge are key to our progress as we build on the insights of those who came before us. The principle of least action is a testament to the power of fundamental principles in physics. It is a unifying concept that connects diverse phenomena, from the motion of planets to the behavior of subatomic particles. It serves as a reminder that a deep understanding of these principles is essential for unraveling the complexities of the universe. As we continue to explore and learn, the principle of least action will remain a guiding star, illuminating the path to new discoveries and deeper insights into the nature of reality.